Okay, welcome to a video about significant figures. What's so significant about significant figures? We're going to learn about what the term means, significant figures, and we're also going to learn how to manipulate them, estimate them, record them. So hopefully this won't take too long. A physicist by the name of Patrick Lynn blogs about this on the internet. Not that you all are out there looking into significant figures on the internet, but he refers to the topic as boring but important, and I can't agree more. This is going to be pretty dry. There are rules that you have to memorize, but they are important as scientists moving forward. So Patrick Lynn has this blog about significant figures, and in there he says that really it's just a way of counting the numbers that we're reporting when we report any kind of mathematical data. He says that there are really two kinds of numbers. There are numbers that are called exact numbers, and then there are numbers that he says have to be decided about using the flowchart of pain. So we're going to not talk about the flowchart of pain, but I just want to let you know I'm trying to spare you that pain. If you read about this in the book, it can be a little bit confusing, so I'm going to try to break it down here into some simple rules that you do have to memorize, but hopefully they won't be too crazy. And certainly I hope they won't be too painful. Okay, so the purpose of using what we're going to call significant figures is to keep track of the quality of a measurement. So you put something on the scale or you read something off of a thermometer, you have to know how many numbers to write down on a piece of paper to convey the reliability of your measurement. Right? So we're going to think about numbers now as not just being mathematical quantities, but also conveying things to other scientists. So how sure are we about our measurement? We're going to make sure that we convey our certainty and our quality and the reliability by looking at the numbers that we assign to each measurement. This is going to include propagating that information through calculations. So often we make measurements, but then we include those measurements in some kind of formula or as some kind of variable. We do calculations, and so we have to know how to add, subtract, multiply, and divide these numbers and carry out their quality or variability. So let's say I put this weird green liquid on this scale I found on the internet, and the scale tells me it's 95.85 grams. That's telling me not only the mathematical mass of this, but it's also inherently telling me something about the reliability of the measurement, right? It is not telling me that this thing weighs 95.85000000. By putting those zeros there, I'm making a statement about the reliability or the quality of my measurement. So I can't make up or add reliability to a number if it's not there. Right? So if I were to add all those zeros, I would be changing the significant figures in my answer. Right? So the scale really tells me it's 95.85. I can't just go throwing on all those zeros. So by not putting numbers, right, by choosing to only put two decimal places, I'm making a statement about how sure I am about the mass of that green liquid. Right? So we only show numbers that we've measured with certainty, or that we get through following a certain number of rules, and we'll talk about those a little more in lab. But I couldn't report this as being, I couldn't report this as being 96, right? That would be me lessening my significant figures, and there's no reason for me to do that. I want to report all the digits that I can with certainty. Right? So all these three options that you see here are different levels of reliability in a number. And I only want to talk about the one that's correct given the instrument that I use to make this measurement. So I would only want to report 95.85. Okay, so if we look at these different kinds of numbers, we'll see that certain digits in these numbers are going to convey certainty, while others are conveying size. So some of these numbers are just placeholders, right? Zeros are used as placeholders in different numbers. Whether or not a number is conveying certainty or holding a place, both jobs are important. It's just that only one of them are considered to be significant figures. So we're not using significant like we would in an English class. All of these numbers are significant. It's just that when we use the term significant figure, we're implying that the number conveys certainty. If we say that a number is not a significant figure, then it's just a placeholder. Okay, so both are important, but we just need to understand the dialogue there. And we'll practice this for the whole semester, and you'll get to the bottom of it. I know it feels maybe new to some of us now. But If I look at the number 12.34, right, all of those numbers are conveying certainty. Each of those digits is telling me it's exactly 12.34. It's just like the scale that we just saw, right? Each of those numbers is telling me about certainty. If I look at 0.134, that 0, right, is just telling us, it's a thing that we do, it's just a convention that we do to tell us that that decimal is coming, right? So it's just to make sure that we understand that we're about to report a number that has nothing in the ones place. All right, so that's not telling us really anything about the number. It's neither a placeholder nor conveying certainty. But these digits here, right, are all digits that are telling us a specific mathematical value about the thing that we measured. So they're all conveying certainty. Okay, over here we have all these digits, but we have this 0 on the end. That 0 is not telling me anything specific, right? They're just telling me that there are no measurements in the ones place of this number, right? And so these are conveying certainty. And by putting that 0 there, I'm holding the ones place, but I'm saying there's no mathematical value to go there. It's just holding the place, right? There's no number to go there. We're just holding the place. And so the same could be said of the last number. Again, this 0 is just telling us that a decimal is coming. That's just a convention. I could write it or not write it. It's good to write it, but I could accept this number without that 0. These zeros, right, are telling me that my number is really little. They're holding the 10th place, right? They're holding the 100th place. They're just saying, wait for it. The numbers are coming, but they're not right here. So these last digits are conveying certainty, and these two zeros are placeholders. So those are two areas where we could put zeros that would be holding places. They can hold places in a whole number. They can hold places in a decimal. All right. So there are some rules. I just went through and arbitrarily told you these are holding places and these are conveying certainty, but you have to internalize the rules so that you can figure that out for yourself. So there are 3 rules. 2 of them are very simple. The last one's a little wacky. The first rule is that any non-zero digit, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? All non-zero digits express certainty about a measurement. So if I look at the number 6.13, those are all non-zero digits. Some are before the decimal, some are after, it doesn't matter. They're all conveying certainty. So this number would be telling me 3 significant figures, right? 1, 2, 3. The number 1,345, same deal. They're all non-zero digits. Thousands place, ones place, doesn't matter. Those are all conveying certainty. 0.966, again, that 0 is just a convention to say there's a decimal coming. 0.966, those are all non-zero digits, so that's 3 significant figures. So this guy would be 4 significant figures, and this guy is 3 significant figures, right? All trapped zeros express certainty about a measurement. So what's a trapped 0 look like? If we look at this number, according to Rule 1, this guy's significant and that guy's significant. If this is a certain part of my measurement and I feel certain about this number in my measurement, then I also must have certainty about all the zeros inside of my measurement. So this would be 5 significant figures, right? The zeros in the middle are trapped, and so they're also conveying certainty. So we have 5 significant figures right here. 308, same deal. If I'm certain about the 3 and I'm certain about the 8, I also must feel certain about that 0. So I've got 3 significant figures right there. And then this guy, the zeros are trapped all over the place, right? This is not a trapped 0. He's just my convention. He's just saying a decimal's coming. So I've got 1 trapped 0. I've got 2 trapped zeros. And so I've got 1, 2, 3, 4, 5, 6, 7 significant digits. So this is a very reliable measurement. I must have had a pretty good scale to get all the way out here to this distant decimal place. So that's 7 significant figures and a very reliable measurement. So those 2 rules are pretty straightforward, right? Any non-zero digit and any trapped zeros. This last rule is a 2-part rule. Both parts have to be true in order for the rule to work. So all zeros that are both after the decimal, so that's telling us where it has to be with regard to the decimal, and they have to be at the very end of the number. It just happens to be a very specific rule, right? It's a rule just like the others, but it's very specific. So if we look at this number, right? Again, this guy's just telling us the decimal's coming. These are significant because of rule 1. These are significant because of rule 3. They are after the decimal, right? And they are happening at the very end of the number. These are the zeros that we tack onto a measurement, not because they're adding any mathematical significance, but because they're telling us that this is a very reliable measurement. This measurement and this measurement are mathematically equivalent, but this one is much more reliable, right? So this would be the better scale. This would be the reliable scale. This scale is only giving us 2 decimal places, and after that it's not telling us anything, so it's a less reliable measurement. This guy would have 4 sig figs, and this guy just has 2 sig figs. Right? So that's what those zeros do for us. They don't change the mathematical face of the number. They're changing how reliable or how certain we are about our measurement. 360.0, right? So same deal. This guy is the magic 0, right? This guy's the one that is both after the decimal and at the end of the number. And so if he's significant because of rule 3, he's significant because of rule 1, that guy's got to be significant because of rule 2. He's trapped. Right? He's trapped between 2 significant numbers. So all 4 of these numbers are significant. Again, we see that we have all these non-zero digits, so we believe the number 117 to be significant. The 0.29 is significant, and that 0 on the end, that's the 0 that says that our measurement is reliable. So we feel good going out to the 3rd decimal place because of the instrument that we use to obtain this number. So that would be 6 significant figures, right? So all 6 of these significant figures are conveying certainty. So there are a lot of zeros that that are not trapped and that are not after the decimal at the end of a number, right? We call those the placeholder zeros. So we saw some of these in the last slide that we looked at. These zeros, right, they are after the decimal. That's good, but they are not at the end of the number. So they are in the middle of the number. These guys are at the end of the number. These are placeholders. These are significant figures. This would be 3 significant figures, right? Again, these are at the end of the number, so they got that going for them, but they are not after the decimal. The decimal, if there was one, would be right here. There's not, so we take this 11,000 to be a whole number, and so this would only be 2 significant figures. These zeros can't just go away. We need them, but we don't call them significant. We call them placeholders, right? 30, again, placeholder 0, holding on to the ones place. There are no ones in this number, but we are holding on to the place, right? We have to hold that place. So this would just be 1 significant figure. We'll talk more about these rules, and I'll give you lots of opportunities to quiz yourself. There's certainly going to be some of these on your homework and some in your first pre-lab that you do. But again, just distinguishing between placeholder zeros and significant zeros, these 3 rules should help you. You just kind of got to stick them in your brain. All right. Just to recap some nuances, right? There are moments when we're not counting significant figures. There's a moment where we get to ignore these rules, right? And they're very few and far between. But if you are counting something that is exact, right? Like I've got 3 apples. Okay, that is an infinitely significant number. There are 3 apples. There are exactly 3 apples. You can't be wrong. There is no uncertainty in that number. So we do not count that as just being 1 significant figure. It's infinitely important and significant, and so we don't apply significant figure rules to exact counting whole numbers. So we wouldn't want to count significant figures there. It just is 3 apples. Likewise, when we're defining conversions, if I say there's 1 foot has 12 inches, then I don't want to look at the 1 or the 12 as having significant figures. I just allow that to be a definition. I really only apply significant figure rules when I've taken a complicated measurement about mass or temperature or energy, right? When I'm calculating something, that's when I want to use these significant figure rules. We'll talk more about that as we move through the semester. Scientific notation, we're going to talk more about this in the next lecture, but scientific notation is a way that we can report really large or really small numbers using a base 10 notation. When you see a number written in this way, right, like 2.460 times 10 to the negative 4, in scientific notation, every digit you write down is significant. So in looking at this number, we would see that I should take that back. Every number written in the base number, we don't look at this, right? We're not going to count any of those digits. Technically, those are numbers too, but we're only going to look at the number that comes before the base 10. So that would be 4 significant figures, right? So that would give us 4. But again, we're going to come back and practice these nuances and these special rules in lecture when we meet again. Everything else, every other number that's not an exact counting number, not a definition, and not scientific notation, everything else is going to follow those 3 rules we just went over, right? We're going to follow those 3 rules about non-zero digits, trapped zeros, and special zeros at the end of a number after a decimal. All right, we're going to use those 3 rules, which are really just a scaffolding to help us distinguish between significant numbers and placeholders. So we're going to every number we calculate, every number we use in a calculation, we're going to think through how many significant figures should be assigned to a number. And we'll talk more about that in class. So what happens when we start to use these numbers of varying significance or varying reliability in mathematical operations? If I want to add these 3 numbers together, we can see that they have varying decimal specificity. So 5.1, whatever we were measuring, we measured the 10th place. Whoever made this measurement with 12 did a crappy job, right? There's no decimal place. They got lazy. That's not a very reliable measurement. We don't have a lot of digits or significant figures after that. And then we have 7.73. So, of course, if I want to add these up, I do addition the same way. I track where my decimal is. I look at my whole numbers. I look at my decimal portions, and I can add these up. Right? So addition's addition. We're not changing that. It's just that we're going to think differently about the value that we're showing and the significance that we're placing on it. So whole numbers in addition and subtraction are always significant. So when I add up 5, 12, and 7, I definitely get to report those numbers, right? I get to report the whole number. But in the decimal portion in addition and subtraction, we are going to be limited by reporting the decimal answer. We're going to be limited by the number with the least number of significant digits following the decimal. So essentially, the weakest measurement, our least reliable measurement, is going to be the one that limits the way we get to show our answer. So if we added all these guys up, we'd get 24.83. That's the math, right? That's what mathematicians would say the answer is. But as scientists, as chemists, we have to go back and we have to acknowledge that this guy was a very unreliable measurement. This number has 1 place of significance after the decimal. This number has 2 places of significant figures after the decimal, and this guy has 0. We took no measurements after the decimal. That is a fairly limited measurement with low reliability, and so I'm going to be limited here when I add up these numbers. I can only report the reliability of my worst measurement, right? After the decimal. That's amazing penmanship. Are you all loving that right now? That's fantastic. Okay, so 24.83. I don't get to say all of that. I get to put no digits after my decimal. So now I'm going to round my number, essentially. I'm going to use rounding rules. I don't get to talk about this decimal portion, but I do get to look at the neighbor and let it round my number. So, of course, if it was a 4, 3, 2, 1, or 0, it would stay 24. If it's a 5, 6, 7, 8, 9, I'm going to round this up. So I'm going to round so that I lose my decimal portion because my worst measurement requires that. And so this real answer is going to be 25. So the trick is in chemistry that you don't get to be a mathematician, right? You don't get to just add up your numbers or follow the numerical conventions. You have to impose this idea about reliability in your number. So every time we take a measurement, We want to show as much certainty as possible so that when we come back here to calculate all the numbers, we get to show the most reliability in our calculations. Right now we're limited because this measurement was pretty weak. Okay, so the final answer here would be 25. It's different in multiplication and addition, right? We're still going to be limited by the weakest measurement, but because when we do addition and subtraction, right, if I were really going to multiply 38.65 by 105.93, right, the way we do that is to multiply each digit by each digit. So I'm going to take decimals and I'm going to multiply them by whole numbers. And I'm going to take whole numbers and I'm going to multiply them by decimals. It's the algorithm that we use to do multiplication. Because of that, I can't do this before the decimal, after the decimal, because all decimals are going to be multiplied by all whole numbers and vice versa. So I have to now, because of that, look at all the digits in the number. Tired of red, let's go blue. Okay, so here, if I look at 38.65, I have to count up the significant figures in the whole number and the decimal portion, right? So that would be 4 significant figures, 38.65. If I look at 105.93, that 0 is a trapped 0, so I have 5 significant figures. Again, we are going to be limited by the weakest measurement. So the least reliable measurement, right? He's the least reliable of the two measurements. So really he's the lesser. I mean, come on, English. What are we doing? The lesser reliable? Yeah, maybe. Okay, I'm not your English teacher. Okay, so there are 5 significant figures in this number, and there are only 4. So over here, we're going to be reduced to 4 significant figures. This is the mathematical answer, right? If we were mathematicians, we'd be done. But we're not. We're chemists. So for now, we're going to have to impose our understanding of reliability. I am not this certain about my measurement because I am only this certain about the incoming number into the calculation. So I need 4 significant figures. Again, I'm going to pick my 4, right? 1, 2, 3, 4. Those are the 4 I get to keep. I look at the neighbor. He's low, so he's not going to change that. So the real chemical answer for this would be 4,094. That's the final answer. If you put anything else, you're going to lose points because I have to help you become not only good at doing calculations, but also good at understanding what we're trying to convey to other scientists as we talk about numbers that we've measured. So we're going to use these rules throughout the rest of the semester. And I'll remind you, and ultimately you'll absorb all of this. And every time we put a number, you'll be thinking about your significant digits. Okay, see you guys in class.